Okay, well, welcome everyone to this second plenary talk for tomorrow's Mathematicians today. It's been a fascinating conference of undergraduate talks. There's fantastic research going on, and we've had one plenary talk so far, and we're very, very fortunate to have Professor Sir Martin Hira from Imperial College London to give the second plenary talk. Sir Martin's has held positions at the University of Warwick and the Courant Institute in New York. In 2014, as many of you will know, he was awarded the Fields Medal in Mathematics and was elected to the Royal Society that same year. Most recently, he was awarded the Breakthrough Prize in Mathematics for 2021. Sir Martin completed his PhD at the University of Geneva under the supervision of Jean-Pierre Ekman in 2001. He's made fundamental advances and contributions in so many fields: stochastic partial differential equations, stochastic analysis, and stochastic dynamics in general. More recently, he's been developing theories in ergodicity of non-Markovian systems, multi-scale analysis techniques, theory of path sampling, and very, very recently introduced a theory of regularity structures. So we're extremely fortunate to have him here. Thank you so much for joining us. And so Sir Martin will now tell us about a mathematical journey through scales.
Okay, thank you very much. And thank you all for coming today. So to start with what I wanted to do, I wanted to sort of discuss a little bit orders of magnitude, right? So an order of magnitude is about a factor 10, typically. And well, so let's see the sort of what's the sort of largest orders of magnitude that you can encounter? So if you think of the universe, right, the smallest sort of thing, what's the smallest thing you can imagine? Well, basically it would be an atom, but actually you can go even smaller, right? You can look at the size of just one elementary particle, like a proton or so. And we have a pretty good idea of what the size of an elementary particle is. And in the other direction, the largest thing that you can imagine is, well, basically the whole universe, right? Or at least the whole visible universe. And if you compare the two, so if you look at the smallest possible thing you can imagine and the largest possible thing you can imagine, there's about 40 orders of magnitude between them, right? Which is actually not a lot if you think about it, right? So like 10 to the 40 is about the ratio between the size of the visible universe and the size of an elementary particle. And if you think in terms of, so that was in terms of sort of linear sizes. If you think in terms of ages, you can do a similar sort of estimate. So on the one hand, you know, the longest duration you can possibly imagine is the age of the universe from the Big Bang until today. So that's sort of the largest thing you can imagine. And the smallest sort of thing you can imagine is maybe like the time it takes for an atom to vibrate, you know, like sort of like the typical time it would take for an electron to go around an atomic nucleus, right? So that's sort of like the smallest type of time scales that you can possibly measure. And again, the ratio between the two is about sort of 10 to the 30 something. And so it means that in some sense, you know, for all practical purposes, anything bigger than about, you know, 2 to the 100 something is essentially infinite, right? So how did I come to, so this 150 is basically 3 times 40 plus 30, right? So because that's a length scale. So if you think of, you know, there are 3 dimensions in space. So that gives me about a 10 to the 120, and then there's time as well. So in some sense, if I sort of take the whole history of the whole universe and I sort of chop it into pixels, where a pixel is sort of, you know, the smallest length that you can possibly imagine for the smallest duration you can possibly imagine, then the total number of these pixels, which describes the whole history of the whole universe, would be about 10 to the 150. So now, you know, you've probably all heard the story of that monkey's paradox, right? Where people say, if you put a monkey in front of a typewriter and you let the monkey type for long enough, then eventually, just by typing randomly, the monkey will produce the collected works of Shakespeare, right? Now, the operative word there is long enough. So if you do a little calculation, what you find out is that the number of letters that your monkey would have to type before having a chance of finding one page of Shakespeare, let alone the whole collected works, would be about 10 to the 4,000, right? And so if you compare that to, like, this was pretty much the largest number we could possibly imagine in some sense, right? In some rather concrete sense. Well, 10 to the 4,000 is really way, 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 way larger than that, right? It's essentially, you know, if you imagine that we had the whole history of the whole universe, we broke it up into these little pixels, which is like the smallest elementary units of space-time we could possibly imagine. If now imagine that in each one of these pixels, you fit a whole universe again, right? Then if you figure out how many pixels do you get then, well, instead of 10 to the 150, you would get 10 to the 300, right? So it would be quite a long way to go before you get to 10 to the 4,000, right? So this is so incredibly large that it's not just infinite. I mean, it's just, you know, completely unimaginably larger than infinite in some sense. So why am I telling you that, right? So the point, what I want to talk about in this talk, is about how things change when you modify the scales, right? When you look at, if you want, the same system, but at different scales. And so what you find is that the laws of nature, they appear to be different from scale to scale. So for example, if you take, you know, one of these little insects, so they're about, I don't know, maybe half a centimeter long or something, and they're perfectly able to walk on water. Right? So they just go to the surface of a pond and they just walk around on top of it. I mean, we are obviously not able to do that, right? I mean, maybe there's some exception, but by and large, humans are not able to walk on water. And the reason why these little insects are able to walk on water is that the equations of motion for fluid dynamics, they are not linear. And non-linear here means that if you actually rescale them, so if you do a change of scale, the various coefficients that show up in the equation change. Right? And the way they change in terms of the equations of fluid dynamics is that if you go to smaller scales, they appear to be more viscous and to have higher surface tension. Right? So viscosity, higher viscosity makes water behave more like honey at very small scales. And higher surface tension means that the surface of the water is much more difficult to break through. And that's basically why these insects don't sink. Now, if you take, you know, some things behave, not everything behaves in a sort of very interesting way as you change scales, right? So if you think of a picture, for example, so take that picture of a teapot and you change scale. So what does it mean to change scale? Just means sort of zooming in. So if I zoom into that picture, I zoom a bit more, well, you see that after a while it gets pretty boring, right? So I started off with a really, you know, nice picture of a teapot with lots of detail, but I zoom in, so this is like maybe 2 orders of magnitude in, and it's just flat, and you see something very boring, just one uniform color. But there are other pictures that are sort of much less boring, right? So that's an example that probably all of you know, which is the Mandelbrot set that was sort of discovered in the 60s by Mandelbrot. And what you find here is that depending on where you zoom in, it actually looks interesting. You know, you can zoom as much as you want, and it still looks interesting. So here we sort of zoomed in about, I think that's the scale up there. So we've zoomed in about 10 orders of magnitude compared to the original picture, and it still looks very interesting. And you sort of zoom in more and more, and it always looks somewhat similar. Okay. but it still has details, right? It doesn't look just flat and boring. I mean, of course, it depends on where you zoom in. If you sort of zoom in here, then of course it just gets black, and then at some point nothing happens. But if you keep on sort of choosing the right regions, then you find interesting behavior at every scale. Right? And that, I mean, of course, this is a very specific example, right? The example of the Mandelbrot set. But it turns out that that sort of feature, so the feature that you see interesting behavior at every scale, is actually pretty common. So it's sort of, you know, if you look at things in the right way, it's a feature that's maybe more common than you think. So for example, you know, here's another well-known example, but it's maybe not quite as well-known. It's called the Lorentz system. So that gentleman here is Edward Lorenz, who was a meteorologist, an American meteorologist. And in the, I think, early 50s, or maybe early 60s, I don't remember, so around that time, he came up with, I think someone has the microphone turned on there. So he came up with this very simple model of atmospheric convection, right? So he was a meteorologist, so he was interested in how the atmosphere behaves. And he came up with this little toy model, which has only 3 parameters. So you have this differential equation in 3 unknowns. And the right-hand side looks very simple. So it's just, you know, this is just a linear function of x and y. Here you have a nonlinear term, right? Because you have this term x times z. And here you have again a nonlinear term, which is this x times y. And even though this system looks really very simple, if you actually solve it, so you take some initial condition for x, y, and z, and then you solve that differential equation and you plot it as a function, you plot the solution as a function of time, you actually find something that looks quite interesting, right? So this is here a plot of the solution as a function of time. So I don't remember, it's like, of course, it's a 2-dimensional plot here. There are 3 coordinates, so I don't remember which 2 it is. It's sort of two of these 3 coordinates that are plotted here as a function of time. And what you find is that the solution does something like that, right? So there are these 2 fixed points here. So there's one here, there's one here. So if you start exactly at one of those, then you just stay where you are forever. If you start somewhere else, then what you do is you essentially sort of circle around one of these fixed points, but your circles sort of get always slightly larger. And then at some point, you sort of switch over to the other one. And then you circle around that one, and then you switch over to this one. You circle a little bit around this one, you switch over to that one, and so on, right? So it sort of keeps on switching. The solution sort of keeps on switching around these 2 fixed points. So you get these 2 lobes, if you want. And if you plot a single solution as a function of time, it sort of goes back and forth between these 2 lobes, but in a sort of roughly random way. And so what you find is that it's, in a way, it's essentially impossible to predict what your trajectory is going to do beyond a few revolutions here. And what do I mean by impossible to predict? I mean, of course, here, you know, it's completely deterministic, right? So this equation, so it's an example of a differential equation, which you've all learned that they have unique solutions at some point in your first or second year of undergraduate studies. And so if you know the initial condition, if you know x naught, y naught, and z naught, and you give yourself a time, well, there is a unique solution, you know where it is at that time, right? And you can do that for any time. But then if you ask yourself, if you want to know at some given time t, on which side you are in that picture, right? So you're going to be at time t, you're going to be essentially on one side of that separation, right? You're going to be either sort of somewhere in this lobe, or you're going to be somewhere around this lobe. And I'm not asking you where you are exactly, I'm just asking you on which side you are, right? Left or right. And if you want to know that for sure after time t, then the question is, you know, like, how precise do you have to know your initial data? It turns out you can actually sort of compute that, or at least it's, yeah, using numerical experiments, you can more or less figure out how precise it is. And that's the answer? So the answer is that the precision you need is about 10 to the minus 0.4 times t. Right? So what does that mean? So it means that if after time 100, you want to figure out just whether you're on the left side of the picture or on the right side of the picture, well, then you needed to know the initial data with a precision of about 10 to the minus 40. But 10 to the minus 40, remember, was about the ratio between the size of an elementary particle and the size of the universe. Right? So it's a completely impossible degree of precision. Right? So even if like that picture that I showed you was the size of the whole universe, then in order to figure out on which side you are after time 100, well, at time 0, you need to have a precision which is better than the size of an atom. Right? So that's what I mean, that it's basically impossible to predict the trajectories, because if you get the initial data wrong by any amount that's measurable at all, then after a relatively short amount of time, you have no clue on whether the solution is going to be on the left or on the right side of the picture. Right? And so even though it's deterministic, you can't really predict the outcome. But then, you know, can you still say interesting things about the behavior of such a system? Well, one thing you can do in that particular case, so there are several interesting things that one can actually still say about the long-time behavior of the Lorentz system. Here is one particular one, which is, well, if you take the first coordinate, so that x coordinate, and you interpret that as a speed, and you plot the corresponding position as a function of time. So basically, you just integrate x over t. And you plot here the integral of x as a function of time, right? So what does it look like? Well, that's what it looks like over a time interval of about 5. And you see here, there's always sort of relatively rapid motion, and then it's more or less flat, and it's relatively rapid, flat, rapid, flat. And that corresponds to, you know, whenever it is turning around one of these lobes, well, the integral is more or less, it goes more or less flat, but then it switches lobes. And that's when it either goes up or down. So you get a picture like that. Over a time interval of 50, you get that sort of picture. Over a time interval of 500, you get this sort of picture. 5,000, this sort of picture. Now, these actually start to look quite similar. So if I were to zoom out even more, it would basically always look about the same, right? It wouldn't be the same picture in the sense that, you know, maybe here it first goes more or less up, and then it goes down, then it goes up again. But sort of the qualitative features of the picture, sort of how wiggly the thing looks like, that would actually always be the same, whichever amount you zoom out by. And the other thing is that you can actually get similar pictures with various other kind of models. So for example, let's take the simplest possible model for something which is random, which is a coin toss, right? So let's just toss a coin, and when it comes up heads, you win £1. When it comes up tails, you lose £1. And say you're allowed to be in debt, so, you know, the amount of money you have is allowed to be negative. And now you plot your money as a function of time. So say first it's heads, so the money in your wallet goes up by £1, then heads again, it goes up by another £1, then tails, it goes down, tails again, it goes down again, and so on. So you get something like this. And now, okay, that's what you get after, I don't know, 15 or something coin tosses. So that doesn't really look the same as what we saw before. But how does it look like after many, many coin tosses? And so if I take this model and I look at what it looks like after 3,000 coin tosses, well, then the picture you see here is pretty much the same as the one that we saw before when we were sort of integrating one of the components of the Lorentz system over time. In particular, for example, in both cases, if you ask yourself, what's the typical size of the what's the typical value, if you want, of what you have in your wallet or your debt, then after n games, it's going to be roughly about square root of n, right? And that, I mean, probably you know why, because that's because of the central limit theorem, right? So you've probably all seen the central limit theorem in some undergraduate course on probability. By this particular case, so this is, if you want, there's some sort of version of the central limit theorem, where you don't just get the normal distribution in the end, but you actually get some kind of random function. And that random function, that was actually described for the first time by Einstein and Smoluchowski in the early 1900s, where they independently, so at the time, there was a famous experiment by Brown, where what he did was to observe particles of pollen under a microscope. And what he was observing is that these little particles were actually moving in some sort of erratic way, even though there didn't seem to be anything sort of external influencing their motion, right? So he sort of waited for a while to make sure that the water wasn't flowing anymore or anything, right? So you just had these little particles of pollen and they were just moving in some erratic way. So in the beginning, he thought they were alive. But then he realized pretty quickly that they weren't. For starters, they were still doing that erratic motion after several days, even though he didn't put any nutrient into the water. And so then he didn't really have a good explanation of what was happening. The explanation that people came up with later was that, well, it was actually random motion that was caused by the collision of these particles with water molecules, right? So of course now we know that water is made up of molecules, which are made up of atoms. And these molecules, they essentially move around sort of like little billiard balls. So they sort of move in a straight line mostly, but then they bounce into each other and they sort of, bounce off each other. And the average speed at which they move, that's essentially what gives the temperature to the water, right? So the temperature of the water is essentially something like the average speed at which these particles move, somewhat like the square of the average speed. And so what he was seeing is that, well, you have this heavy particle, which is like this grain of pollen, which was being bombarded from all sides by these molecules of water that were sort of hitting it at pretty high speed. And then for each collision doesn't really have much of an effect, but overall they actually add up and you still see some kind of macroscopic motion. And so that was reasonably sort of well accepted as an explanation, even though at the time the fact that matter is made up of atoms wasn't completely clear, right? So it wasn't, so that was still somewhat controversial in the late 1800s, right? So it was somewhat, it was more or less the accepted hypothesis, but there hadn't been any experiment that was impossible to explain in any other way. And what Einstein and Smoluchowski realized was that, well, not only the atomic hypothesis was explaining what Brown saw, which is something that people had already realized before, but you could actually make kind of quantitative predictions out of it. You could actually figure out by how much, your grain of pollen would move in a given amount of time. And then you can actually make an experiment out of that, which is what Perrin did in 1908. And his experiment, verified to pretty decent accuracy the predictions of Einstein and Smoluchowski. And so that was really what actually settled the debate about the existence of atoms, right? Because at that point you had an experiment which clearly couldn't be explained in any other way. And so, everybody accepted, if you want, that matter is made of atoms. And Perrin got the Nobel Prize for that experiment, actually. Now, there's a completely different story where essentially the exact same process shows up. So so Bachelier, so he was a young French guy who wrote a thesis in 1900, so around the same time as Einstein and Smoluchowski wrote their articles. And in his thesis, he wanted to explain the evolution of stock prices. You know, like he wanted to explain the behavior of the stock market. And so he came up with an explanation, which was pretty much the same as the explanation of Brown's experiment, in the sense that what he was saying is that, well, what influences stock prices? It's people buying and selling shares. And every time somebody buys or sells a share, well, if somebody buys a share, then that drives the price slightly up. And somebody sells a share, it drives the price slightly down. And so every single transaction doesn't have much of an effect on the stock price, but there are many people buying and selling shares. And so altogether, there is still an effect, which you actually see in the sort of macroscopic, if you want, evolution of the share price over time. And so on the one hand, you see that, you know, the flavor of the explanation is pretty much the same as before, in the sense that you have a quantity which is influenced by many different random and sort of independent events. Each event doesn't have much of an effect, but the cumulative effect is sufficiently large so that you can actually observe it, right? And so in both cases, both Einstein, Smoluchowski and Bachelier came up also with a, you know, mathematical equation that actually describes the evolution of the probability distribution for, on one side, the position of the particle of pollen, and on the other side, the value of the share price as a function of time. And in both cases, the equation they came up with is what's called the heat equation, right? So the heat equation, I don't know if maybe you've seen the heat equation. It's sort of, if you have a function u, which depends on x and t, so that will be your probability of seeing the particle at time t at the location x, or if you want that at time t, the share price has value x. And the equation is that the time derivative of u is equal to the Laplacian of u. So if you want the sum of all the second derivatives in space. Right, so that's the heat equation, which comes up in both cases independently. And so that in that case, well, that basically laid the foundations for what's now called the Black-Scholes model. And well, that's a, you know, it's a very basic model for modeling the stock market, but it's a very important model because most other models essentially start from there and then build on that, on top of that. And Black and Scholes got the, well, economics Nobel Prize for that in the 90s. So what was the point here? So the point was that you have one relatively simple mathematical model, which is this random continuous function, which sort of looks in a very wiggly way, which I've showed you sort of twice now. It sort of, you know, typically looks like something like this. Which people call Brownian motion, or sometimes Wiener process, because Wiener was the first to actually give a full mathematical description of this object as a probability measure on a space of continuous functions. So you have this mathematical object which shows up in various different contexts that appear to be somewhat unrelated, right? So on the one hand, you take that Lorentz model of, you know, atmospheric convection, you take the first component, you integrate it up, and you get something which is that Wiener process. Then you take coin tosses, you just add up the values, you know, +1 for heads, -1 for tails. You plot it as a function of time. Again, you get the same thing. You look at, you know, pollen under a microscope, you look at the motion of pollen under a microscope. Again, it's described by Brownian motion. You take these stock prices, at least over short time intervals, they're pretty well described by Brownian motion. Okay, so you have this one sort of somewhat universal object, which is Brownian motion, that shows up in many different contexts that seem to be, on the one hand, they're unrelated, right? On the other hand, you do sort of feel that there's a relation, right? Like in all cases, there's something about, you know, adding up lots of independent things somehow, right? So they have a flavor which is similar to the flavor of the central limit theorem. And so Wilson, in the so he was a very famous theoretical physicist. And so in the sort of 70s and 80s, he came up with a theory, or it isn't so much of a precise theory, it's more of a philosophy of how to think of these things. And so his point of view was to say, well, you should really somehow think of physical theories as being like some sort of giant dynamical system where time is really, should be thought of as the operation of changing scales, right? Looking at different scales. And so you take one physical theory, you scale things either up or down. You look at either you zoom in, you look at what happens at small scales, or you sort of zoom out, you look at what happens at large scales. And while you find that, you know, what looks like one theory at one scale might start to look like a different theory at other scales. And so you have some kind of a dynamical system in the space of all physical theories. And well, the interesting point, if you have a dynamical system, the interesting point of your state space, which here would be like the space of physical theories, the interesting points are the fixed points of the dynamical system, right? So here it would be the physical theories that behave in the same way, no matter what scale you're looking at, right? So those are, so the idea is that those are the theories that are interesting because you're more likely to actually see them, because they would somehow persist over large ranges of scales. Right? And then it's more likely that the scale at which you happen to actually look at a system would fall somewhere within that large range of scales. Now, the other insight that Wilson had was that actually there probably aren't all that many of these fixed points, right? And so one can try to maybe either classify them or at least, you know, understand them, or try to make some sort of a theory of these fixed points. Right? And that idea, that turned out to be, you know, very much a guiding principle for, you know, theoretical physics for the past 40, 50 years or so. And, you know, to some extent, that Wilsonian philosophy sort of maybe explains to some extent what Wigner called the unreasonable effectiveness of mathematics in the natural sciences. So the point here being that, well, you know, there are many physical theories that you could look at, that you could write down. And in some sense, it doesn't matter so much what is the theory of everything that would somehow describe the whole universe as one unified theory. Because what happens is that these theories sort of, you know, whether you zoom in or out, depending on which scale you're looking at, you kind of end up seeing different effective theories anyway. But there are only relatively few of those. And therefore, at the end of the day, there are somehow a relatively manageable number of somehow mathematical theories that end up describing what we see around us. Right? And that somehow, maybe to some extent, goes in the direction of, you know, explaining maybe to some, in some sense, why mathematics has been quite successful at actually describing nature, even if, you know, the equations that you're writing down are not don't necessarily have the ambition of being a full description of what's actually going on. Right? So now in the last sort of 5 minutes, let me sort of go a little bit beyond that Brownian, what we call universality class, right? So here, what's a universality class? So in this Wilsonian picture, that is, you have these fixed points that correspond to interesting theories. And then these fixed points, they have basins of attraction. So there are many theories that would have the property that if you zoom out, then they would converge to one of these fixed points, right? Which is one of these interesting theories that don't change anymore, whether you zoom in or out. And so one of those fixed points was Brownian motion, right? So Brownian motion is, a continuous random curve, which is self-similar in the sense that, you can zoom in or zoom out as much as you want. It always looks the same, right? It's not the same curve, not like a straight line where you can zoom in as much as you want. It's always a straight line, and it's literally the same curve. In case of Brownian motion, it's statistically the same as you zoom out or in. But there are other interesting, mathematical objects that have the same properties and that do arise in nature in somewhat similar, in slightly different contexts. So one of them is one that shows up in interface fluctuation models. So the situation here is that you have two regions in 2 dimensions, and they are separated by, an interface. And you're in the situation where one of the regions is sort of more stable than the other one. So one of them invades, if you want, the other one. So the example is here like a bushfire, where you see, well, here's the region that was burned, here's the region that's not yet burned, and here's a flame front, which is the interface between these two regions, right? As another example here, which is an example from where you take a liquid crystal, and the liquid crystal also comes in somehow 2 different phases, and they have different optical properties, and so you can literally see the difference under a microscope. And so one of them shows up darker, one of them shows up lighter, and one of the 2 is more stable than the other one. I think here in that experiment it was the dark one that's more stable. And so it means that this interface here, so that region that separates the dark one and the light region, that's actually going to move up, right? Because this one's more stable than that one. And so it's going to invade this region. And so this interface sort of here, it's in this location. And then after a while, it's going to be here. A bit later, it's going to be here. And what people are interested here is not so much, so there's several questions you can ask. So one is, like what's the average speed at which that interface moves? And well, that's just going to be some value which depends on context. So it doesn't have anything universal about it. But then you can ask yourself, what do these fluctuations actually look like, right? And so here there are fluctuations not only in space, but also in time, right? So it's like, here, you should think of these as being snapshots in a movie. So here is a very simple toy model that's supposed to describe have the same features as these 2 similar systems. And so I can actually give you an actual simulation. So the toy model here is what I would call the Tetris model, right? So you think, so here you just see Tetris bricks. And you should think of these bricks here as falling down, but nobody is playing the game. And so they're just piling up, right? And so here you see this big pile of Tetris bricks. But now what's interesting is to see what happens at large scale. So here you can zoom out. And so you see more and more of these bricks. They kind of pile up. And if I zoom out to sort of, quite large scales, what I see is that I have one of these interfaces, right? So I have Tetris bricks at the bottom, no Tetris bricks at the top. The Tetris bricks invade the no Tetris brick region, right? Because they kind of fall down from the sky and they just pile up. So you have this interface that separates the two regions, and you see that this interface is not flat. Right? So you clearly see that on the screen. And in terms of how it fluctuates, it actually looks not dissimilar to, all of these two interfaces. And actually you can make, you can measure more precisely features of these fluctuations, and you find that they are really the same, in the sense that, for example, the probability distributions that show up naturally in terms of, where is the location of the interface, they are not Gaussian, unlike in the case of the central limit theorem or in the case of Brownian motion. And so here, there is the situation where you actually have, so what one finds is that there are actually two sort of universality classes in this case. So there's because what could happen is that you can also look at situations where the two regions are symmetric, right? So where it isn't the case that one of them invades the other one, but fluctuations can go both ways and they're symmetric in both ways. And it turns out in that case, the fluctuations tend to be Gaussian again. And then that's what's called the Edwards-Wilkinson universality class. In this case, it's some sort of extension of this Brownian motion where instead of just depending on time, it depends on space and on time. But still, everything is somehow Gaussian. But in the asymmetric case, where one region invades the other one has a different universality class. So that's called the Cardass-Parisi-Jam universality class. So it's named after the three physicists who first described it in the 80s. And by the way, Parisi, he actually got the Nobel Prize last year, but not for that, for some different work that he did. I guess this was actually mentioned also. So you have these two natural objects here, one which is called the Edwards-Wilkinson fixed point, one which is called the KPZ fixed point. And so these are, again, we can describe them. They are two random spaced functions that depend on space and time, except that now the description is actually much more difficult. So in one case, it's very simple. So this, in the symmetric case, this Edwards-Wilkinson universality class, one has a very explicit description in terms of Gaussian densities. This KPZ fixed point, turns out, was actually only described about 4 years ago. Okay, so this is actually very, very recent mathematics. Although, it shows up in very natural and somewhat simple situation, like this toy model with the Tetris bricks falling down. By the way, for that particular model, or even simplified versions of that model, one still doesn't have a mathematical proof that the behavior at large scales is really described by this KPZ fixed point. So that's still a very hard mathematical problem. One thing that one can describe, though, is that, again, in this Wilsonian picture, you have these fixed points. One can ask oneself which one is more stable than the other one. So it turns out that in some sense, that KPZ fixed point is more stable than this Edwards-Wilkinson fixed point. And then you can ask yourself, is there an orbit that sort of connects them? So that corresponds to, is there a physical model, or mathematical model, if you want, which has the property that if I zoom in, then it converges to this Edwards-Wilkinson fixed point, and if you zoom out, converges to this KPZ fixed point. And there the conjecture was always that there's basically one. There's exactly one model which has these two properties, and which is called the KPZ equation. And that's a stochastic partial differential equation that one can write down. So it's relatively simple to write down. But it's kind of problematic because this term here, it's called space-time white noise. So it has the property that if you look at, it's if you want some sort of generalized Gaussian function, which has the property that the correlations are just delta functions in space and time. So it's extremely singular. And so it means that the solution to this equation is quite singular as well. And in particular, it's so irregular that the slope is infinite everywhere. But then here in the equation, you've got the square of the slope showing up. So that's a problem, right? So since that's supposed to be infinite everywhere. So actually, you have to subtract an infinite constant here. And then it's really not clear what that actually means, right? So here there's a sort of recent series of results which I was involved with a number of co-authors, where we showed that, well, on the one hand, we gave a notion of solution to these kind of equations, but also we show that they're quite stable under perturbations, and we show that they have certain universality properties. So in particular, it goes in the direction of, proving this conjecture that there is really exactly one model which interpolates between this Edwards-Wilkinson universality class and the KPZ universality class. Although that statement, as it is, it still hasn't been proved. So we have rigorous statements that go very much in that direction, but it's not a full proof of that conjecture. And I think this is a good point to stop. And thank you very much for your attention.
Oh, thank you so much for that fascinating talk. I could have gone on listening for a lot longer, but I'm just having a look at the chat. Do we have any questions at this point? I have one, if I may, and I'm not too sure if this relates to what you were saying, but I was reading something, I think, by another physicist, perhaps Sean Carroll, a little while back. And I'm just wondering, does things like emergent properties of system come out of this work? And so what I mean by that is, if you zoom in really close, you don't really see any behavior of a system. But then if you zoom out, you can really say that the system exhibits a kind of behavior, and the equations are easily modeled on a more global level than a more local level.
Yeah, it goes in the same direction, right? So you're trying to, you have models where you have relatively simple rules that govern them at the microscopic level, and then you're trying to understand what's the kind of large-scale macroscopic behavior that emerges from that. So yeah, I mean it does go very much in the same kind of direction. Yeah.
And I was just trying to think how fixed points fit into that kind of emergence, or does it make sense to talk about fixed points with emergent properties of systems?
It probably depends a bit on the system, and it probably depends a bit on how you're describing the large-scale behavior, right? And what sort of features are actually kind of stable as you look at it at larger scales.
Right. Okay. Thank you. Okay. Any other questions? Feel free to type in the chat or unmute yourself and fire away. It has been a very long 2 days of a conference, so and it's been online, so maybe there's a little bit of conference fatigue, but also people may be waiting for some announcements of some prizes. There's a question that just come in. I will try to see.
Oh yeah. How do you get a sense if there is actually structure present in stochastic systems? Is it intuition or the heuristics you use? Well, okay, so one thing that you do use is, I mean, or at least personally, I do sometimes use sort of little simulations like the one I just showed you with the Tetris bricks, right? So you just, try to see what happens. And then you just check if you want, and whether you see something interesting at larger scales or not. And then if you see something interesting, well, then you can ask yourself, is that something that people have seen before? Have they described that? Is there a mathematical theorem that exists that actually describes that or not? And so there is some part of experimentation, if you want. There are heuristics as well. I mean, physicists have come up with a whole range, of course, of heuristics of how to figure out, how these systems behave at large scales. And by and large, these heuristics work, right? I mean, in the sense that in most cases, they would give you the right answer. On the other hand, they're also, by and large, not terribly well understood mathematically, in the sense that, it's quite difficult to actually get rigorous mathematical theorems that would encapsulate some of these heuristics. Right?
No, thank you. So just having a look at the time and the schedule, I think if there are no more questions, can we please thank Sir Martin again for his time and a wonderfully lucid talk.